Hi, in this video of import, we are going to be discussing the Gaussian substitution method. Recall that the Gaussian substitution method is a universal method, but in this present context, we're discussing it for m equals to n and determinant a not equal to 0, because like I said, when those two conditions are met, you can use either of the three methods: Cramer's rule, matrix inversion method, or the Gaussian substitution method. Please note that this is a very important method to understand and to be able to do, because its applications are in different chapters forthcoming as well. So please consider this as an important concept and make sure that you practice it ample enough so that you don't make a mistake when you are applying it. Anyway, let's get started. So you have the following saying: solve using reduction or the Gaussian elimination method. It's also called the Gaussian substitution method. Essentially it has to be the Gaussian method. Essentially that is all you need to know. Okay, so again, you have taken a system of equations. You have three equations here: x plus y minus z is equal to 9, y plus 3z is equal to 3, and x minus 2z minus x minus 2z is 2. Okay, so the first step once again remains the same. You write out the coefficient matrix. Now, instead of writing simply the coefficient matrix, you write what is known as the augmented matrix. Now, the augmented matrix is an important matrix because so essentially, the augmented matrix is just the coefficient matrix with an added column of the constants. Okay, which is the constant vector, which is 932 in this case. So you write out the normal coefficient matrix and you add an additional column, which is the constants vector, which is 9, 3 and 2 respectively. Okay, so this is known as the augmented matrix because you're simply augmenting the coefficient matrix by an additional column. Okay, and the idea is that you now work with this augmented matrix to automatically arrive at a solution. So the idea is that when the coefficient matrix, takes a particular form, then what is left of, or rather becomes of, the column vector of constants is precisely the solution to this system of equations. Okay, so essentially what you're doing is that you will perform some row operations. Perform row operations such that the coefficient matrix takes a particular form. Okay, once the coefficient matrix takes this particular form, the changes to the column vector right here is exactly what is going to give you the values of x, y and z. What this particular form is, I'll come to very shortly, but essentially the idea of this entire Gaussian method is to perform row reductions and row operations such that you can get the coefficient matrix to a particular form so that you can conclude on the values of the variables x, y and z. And for this you write down, the first step is to write down the augmented matrix. Okay, the next step is to make the matrix, this particular matrix right here, a matrix equivalent to its upper triangular form. Okay, upper triangular form. Recall that the upper triangular form was simply that for all so this is I21, which is I greater than j. So for all I greater than j, aij has to be equal to 0. Okay, So if this condition is satisfied, then you have an upper triangular matrix. Again, recall that in an upper triangular matrix, all of the weight of the matrix falls on the upper triangle, which means that the lower triangle is full of zeros, which is why you're able to write this definition right here. Okay, so you try to make the following matrix an upper triangular matrix. Okay, now for this matrix, clearly if you look here, to make it an upper triangular matrix, the steps are very simple. You already have two zeros here, so you just need to make this a zero. How will you make this a zero? You will add this in this row so that this becomes a zero. -1 + 1 is 0, right? So R3 goes to R3 plus R1, okay, which is what you have here. Now, but when you do that, when you say R3 goes to R3 plus R1, 0 plus 1 becomes 1, okay, which means that you have a 1 here now, okay. The reason I'm not writing this out, myself here is because I know I will write down a very ugly matrix. That is why it is better that you follow the steps from the pictures. Okay, so you do R3 goes to R3 plus R1, you're left with this particular matrix right here. Okay, then after this you now need to make this a 0, right? So what will you do? You say, okay, R3 would now go to R3 minus R2. Okay, so this 0 remains as it is. 1 minus 1 becomes 0. -3 becomes -6. Okay. Now this is an upper triangular matrix. Yes. Because if you look at the principal diagonal, this is right here, the principal diagonal. All the elements below the principal diagonal are actually 0. Therefore, it is an upper triangular matrix. Yes. Okay. The next thing that you want to do is make sure the first non-zero entry of every row is a positive number, is a positive 1, not a positive number per se. I mean, obviously 1 is a positive number, but the number in particular also has to be 1. Okay. Now this is a step which is, it's kind of, I say, optional, because even if this is not true, the next step, I mean, if this is not true, then the next step becomes a little more difficult for you. But, you can also choose to not try to do this at some point. But this is the most important part. You get it to upper triangular form. Otherwise, it becomes very difficult to solve the system of equations. Okay. So once you do this, in this case, because I can very easily do this just by dividing it by -6, I'm going to choose to do it. Okay. And you just say R3 goes to R3 into -1/6. Please understand and remember that all you are saying is that the first non-zero entry has to be a positive 1. You're not saying anything about the rest of the entries. So all you're saying is that for all I greater than j, aij has to be a 0, and for every leading non-zero entry in every row, it's an ideal scenario if it were to be equal to a positive 1. Okay. So now that you've achieved this form right here, where you are dealing with a upper triangular matrix, every row has the leading entry as a positive 1, then simply what you do next is open this system of equations out. So recall that you got this matrix from this system of this particular system of equations right here. You use this system of equations to write this matrix. Now I'm saying use this reduced matrix, so to say, to write out the system of equations again. And through simple substitution, you should be able to solve the system pretty easily. So this I'm going to do right here. Let me just change colors. So you have x plus y minus z is equal to 9. You have y plus 3z is equal to 3. And you have z is equal to -8/6. Okay. So since you have z is equal to -8/6, you have y plus 3 into -8/6 is equal to 3, 3, 2, 4. So y minus 4 is equal to 3, y is equal to 7. Okay. So you have y is equal to 7, z is equal to -8/6. And now you just substitute. So x plus 7 minus plus 8/6, okay, is equal to 9. So you have 6x plus 42 is equal to 54 minus 8. Yes. So you have 6x is equal to 54 minus 50. 6x is equal to 4. X is equal to 4/6. Okay. So this is your solution. You have x is equal to 4 upon 6, y is equal to 7, z is equal to minus 8 upon 6. The same thing that I just said in a slightly cleaner form right here. You have the same values, okay? So this is, how you solve it using the Gaussian method. Understand that the Gaussian method, while it seems a little unfamiliar, is extremely easy to execute once you get the hang of it. So I would suggest more and more practice, increasing amounts of practice to sort of familiarize yourself with the way it works, and so that you don't sort of get confused in forming the upper triangular matrix, because that is the key to this entire exercise.